In this problem, we inject 15 grams of liquid water into an evacuated container. It has a volume of 150 milliliters. We seal off the container, we heat it, and after we've added 11 kilojoules, the question is, what's the final pressure in the vessel? So we're starting off, we have a fixed volume container, 150 milliliters, and 15 grams of liquid water, which is about 15 milliliters, so about 10%. Now, some of this is vapor, but the amount is really small, so almost all of the water is in the liquid phase. And so this is starting at 25 degrees C. We're going to add heat, and let's write down that we have 15 grams of water and the volume 150 milliliters. So we're going to use the first law, closed system, delta U equals Q. There's no work. But we're going to do this balance. This is important. We're going to do it per kilogram so we can use the steam tables. And so that means if I calculate Q, it's 11 kilojoules, but the number of kilograms is 0.015 kilograms. So 733 kilojoules would be added per kilogram. So in addition to using the first law, we're going to take advantage of the fact that the volume is fixed. And the volume, 150 milliliters, again, this specific volume, so it's per same number of kilograms. Then we're going to do units conversion. And so calculate the specific volume. And we're going to use the fact that when we finish heating, the specific volume hasn't changed. The amount of liquid vapor certainly changed. As we heat, we evaporate some of the water, and we're raising the pressure and the temperature. But at the beginning, at 25 degrees C, when we start, the specific volume allows us to calculate the quality, namely 1 minus Q, where Q is the quality, times the volume per kilogram of the liquid phase, plus the quality times the volume per kilogram of the vapor phase. I'm going to pause and write down these values that I get from the steam tables. So here's the spreadsheet for steam tables, where I put in temperature 25 degrees C, and then the volumes that I use in the calculation, liquid volume, the vapor volume, and then internal energies, liquid internal energy and vapor internal energy. And then in this spreadsheet, I can use the quality calculation that's on the right. So if I put in the quality 0002, then I get a specific volume close to 0.01. It's not necessarily getting more accurate than this because essentially we have almost all liquid. The value then of 105.2 is close enough. That's what I've used in the calculation. So here's the spreadsheet that I used, that I just showed, and I'm going to use a procedure. I want to find the final temperature and therefore the final pressure. So I'm going to guess the final temperature. I'm going to use the fact that V is constant, the specific volume, to determine the quality. I'm just going to use the spreadsheet I just showed you. Very quickly can figure out the correct quality to give me this value for V. Once I know V, the same spreadsheet also shows me the value for U. And so what I'm going to do is pick a few temperatures, and I'll just show a couple to narrow down the answer. So here's some values for temperatures, and now let me go back to that first law of U2 minus U1 is equal to Q. So U2 should be, the Q value was 733 kilojoules per kilogram, and then we add 105.3. So 838, that's how much the internal energy should be when we've added this amount of heat. So what I've done is try temperatures, and I tried more than I'm showing you here, but I narrowed it down to at 178 degrees, Q is still a small fraction, only a little more than 4% is in the vapor phase. But now I have U2, 834. That's close enough. We don't need three significant figures on the temperature. So I now know the final temperature, and add that temperature from the steam tables. Of course, I can just read off the saturation pressure, which to two significant figures is 0.96 megapascal. So as we've added the heat, much of the heat goes to raising temperature of water, and some of it goes to evaporating 4.4% of the water, putting in the delta U of vaporization.